Okay, remember last time I said I was going to do some further examples on titrations. These I'm going to do two. This is not a very long video, but I'm going to just go through them quite slowly. Once again, I'm going to use the method I prefer, which is just to put it all into a table, because it kind of it makes it easier for me to sort of grasp it, because I can see immediately what I know and what I don't know. So let's have a look. This is question 3, C and D that we're going to do now. All right. Well, let's have a look. They say here on question 3C, a volume of 20 centimeters cubed of a 0.25 mole per cubic decimeter HCl is used to neutralize 25 centimeters cubed of a Na2CO3 solution. Right? Calculate the concentration of the NaOH and the mass of the Na2CO3 that was in the solution. Right? Well, let me just go to my where I've written it down here, and let's have a look here where we basically what we're saying is that we're going to have HCl and Na2CO3 that are added to each other. So let's write down what we're given. All right, over here, just check that we've got it. Yep. So let's write down HCl plus Na2CO3, and because it's a neutralization, we're going to get NaCl plus CO2 plus H2O. Okay, standard. There's our gas, and let's have a look. There we've got an acid plus a carbonate. Remember, those are the theory bits and pieces we've got to know. So let us just have a look. First of all, well, let's balance it. We've got Na, so we balance that. HCl, NaCl, Na plus 1 and Cl minus 1. So we're fine on the small numbers. One of my students calls them the baby numbers. We're fine there, so that's all cool. Na2CO3, 2 Nas, which is fine. And all we've got to do is now we're going to use 2 Cls. So we've got 2 HCls there, so we can balance the Cls. And basically, let's just see. CO2Os, C is balanced. There we go. Okay. Now let's have a look and see what is the ratio. The recipe plus 1 goes to 2 plus 1 plus 1. And let's see, what are we given? Well, on the given stakes, we're given 20 centimeters cubed, given, I'm just going to put it down here, molar mass, N number of moles, concentration, N over V. So let's say given, we've got 20 centimeters cubed. Okay. Immediately, we have to change that over to cubic decimeters, correct? So it's centimeters cubed, we're going up 1. It's a volume we divide by 1,000. That is 0.02 decimeters cubed. Right? Now let's have a look at the next one. 25 centimeters cubed over here. Once again, we've got to change that to 0.025 cubic decimeter or decimeters cubed. And let's have a look. Right. Now they say that they've given us a concentration, right? Concentration, they've said, of the HCl was going to be, well, let me just go back and check exactly what we've got. They say that the volume of that of a 0.25 HCl is used to neutralize that. So we know that that is 0.25 moles per cubic decimeter. Like so, 0.25 moles per cubic decimeter. So now we can see, well, straight away, glaringly obvious, the most information is on the HCl line, isn't it? So let us now proceed with that. Let's say, right, use always the most information we've got and move forward with that. What can we calculate? Well, we're given a volume. V is known. Right? So if we know V, we can say that 0.25 is equal to N over 0.02. Therefore, N must be 0.02 times 0.25, right? So we've got there, that is going to be number of moles 5 times 10 to the minus 3 moles. All right? Now, here, once we've got moles, what do we say? Well, the moment we've got moles, we apply the ratio at this point. And we need 2 as to 1. So what are we going to get when we take this through? That's going to be 2 over 1. That's going to be 2.5 times 10 to the minus 3 moles. Because we need them to react in 2 to 1 ratio, don't we? 2 parts of HCl to 1 part of sodium carbonate. Let's have a look now. If that is the case, then we say, okay, well, let's work out the concentration. Go down. Concentration is 0. Let me write it in scientific notation. 2.5 times 10 to the minus 3 moles divided by 0.025 decimeters cubed, and that's going to be equal to 0.1 moles per cubic decimeter. The second part is they say, well, what was the mass of sodium carbonate that was dissolved in there? Well, let's now work back. We are given that. How do we work out a mass? We haven't worked out a molecular mass yet. So if we work out the molecular mass of sodium carbonate, because that's the one we're working with, right? So let's just use it. So we've got 2 times sodium carbonate is 23, 2 times 23, plus the 12, plus 3 times 16 is going to be equal to 106 grams per mole. And we know that we've got 2.5 times 10 to the minus 3. So let's work out therefore, okay, all right, let me go back and go back down over here. Therefore, we know that the number of moles is mass over molecular mass, which is then therefore going to be equal to, well, let's put in what we know. We know that it's 2.5 times 10 to the minus 3 moles is equal to mass over molecular mass, which is 106 grams per mole, right? Therefore, we cross multiply and we can work out that the mass is going to be 2.5 times 10 to the minus 3 multiplied by 106, which gives us 0.265 grams. Right. Pretty straightforward in that situation. Okay. Now, let's just have a look at the next one now. Now, the next one is a slightly more advanced one because, let's just read it here. They've said to us over here, they've said here, this is 3D, a 0.5 mole, the capital, right, HCl solution is titrated with 50 moles of a 0.5 mole NaOH solution. Calculate the pH after 30 moles of HCl has been added. So let's just examine what are we doing here. We are taking an acid and we're taking a base and we're putting them together. So we're going to get a salt and water. We're doing a neutralization reaction. We're titrating the acid into the base. So we've got a base over here, right? And we've got our acid over there, and we're going to run the acid into there. Now, at this point, we're not going to an end point because they've asked us calculate the pH, right? So we're going to be neutralizing. Remember what this does. As the acid's dripping into the alkaline, the base rather, as it's dripping in, it's doing a neutralization process, isn't it? The acid is neutralizing the base. Well, first of all, let's have a look at what the reaction is going to be. All right? We know that in this situation over here, the reaction, let's just write it down, okay, is we say, okay, HCl plus NaOH. HCl plus NaOH, right? That is what we're doing. That is giving us NaCl plus H2O. All right? Now, let's put down ratio first. The ratio in this case, and just for a bit of change, it's going to be 1 plus 1 gives us 1 plus 1. Okay? Now, let's put down given. All right? Given, we've got 50 mol of that. And we say 30 moles of this are used, right? Let us look at molecular mass. Molar mass is going to be 36.5, 35.5 plus 1 is 36.5 grams per mole over there. And it's going to be our sodium hydroxide is 23 plus 16 plus 1 is going to give us 40 grams per mole, right? So we've got our molecular mass. Now what have we actually done, right? Let's have a look here and we say, okay, last bit we're given concentrations is going to be 0.5 m and 0.5 m, okay, which is 0.5 moles per cubic decimeter and 0.5 moles. I wrote it the two ways on purpose so that we can just see there's no difference between the two. Right, what are we going to do next? Next we're going to say, okay, let's see, okay, N is our line over there. What have we got? We've said here, if you look, can you see that once again we are given two reactants? And remember what we said is when we've got two reactants that have been given, there's a possibility that we could have a limiting reactant approach. Well, this is similar in the vein of we haven't fully neutralized this. We've in fact added the acid to the alkaline so that the pH of the alkaline, or the base, has dropped, right? Because of the acid that we're adding. But it hasn't totally neutralized it. So we need to find out what the resulting pH is going to be. So what we've got is we've got 30 moles, okay, of our acid is added, right? So let's take this first of all and we say, okay, let's just go down. Let's convert 30 milliliters, shall we? Whoops. 30 milliliters, all right? Now we've got to get that up to decimeters cubed. And remember, we've got that little triangle thingy, all right? Now in this case, however, we've got milliliters, okay, centiliters, deciliters, up to liters. So let's go up. Now we're converting moles. We're going to be doing each one of these, 10, 100. We're going to be dividing it by 1,000, okay? First of all, I'm going to just make this liters. So 30 moles over 1,000 is going to be 1, 2, 3. 0.03 liters. And remember, 1 liter is 1 cubic decimeter. Therefore, this we can say is 0.03 decimeters cubed. Right? Let's change them all to the same. Okay. Let's just change those quickly. 30 moles is 0.03. And let's change the 50 at the same time. The 50 is 0.05. Okay. Okay. Now, let's see where we go now. What have we done? We've now said, okay, 30 moles or 0.03 decimeters cubed of this are added. How many moles is that going to be then? Well, concentration is N over V. Well, concentration is 0.5 moles per cubic decimeter, and we've added so many decimeters. So how many moles have we added? We can say that that is going to be equal to 0.5 times 0.03, which is going to be equal to 0.015 moles. So we've added our 30 moles. That has given us 0.015 moles. Now, that 0.015 moles, this is the part, is that is reacted with how many moles of the other stuff? Well, let's see. That has reacted with, and it goes 1 to 1, doesn't it? Remember, what do we say? At this point here, we apply ratio, or the recipe. Therefore, in a 1 to 1, that must have neutralized 0.015 moles of that. All right? But now we had that was a 0.5 and there was 50 moles. So let's have a look how many moles was there. Right? Because if I can find out how many moles were in the beginning, let's have a look. Once again, we had 0.05 decimeters cubed. Therefore, number of moles in my sample is 0.5 times 0.05, which is going to be equal to 0.05. I'll just check. 0.5 times 0.05 is going to be equal to 0.025 moles. Right? So let's just look. What have we got at the top here? Okay? Let's just go here. What has happened there? 0.015 moles of acid has neutralized 0.015 moles of the base, which therefore means that we have got left. We've got some left. How much have we got left? We have got, let's just work it out. Okay. Let's go back and have a look at a different kind of concept here. Let's say we started with how many moles of acid? We started with 0.015 moles, right? Then we used 0.015 moles. That was our 30 mol. And that started with 0.025. Point 0.025. That is this figure right over here. It's that figure over there. So now let's go further. Therefore, we neutralized 0.015 left over 0, left over here 0.01 moles. Right? Now, so there's 0.01 moles left of the NaOH. That is what is left over in there. Now, if we just think about it, that 0.01 moles, we have 0.01 moles of NaOH. What is that again? Well, we know that NaOH, okay, in water is going to go into Na plus OH, right? Plus, and that is at a ratio of 1 goes to 1 plus 1, like so. All right. Let's now put in what are we given? Given 0.01 moles. Therefore, how much OH do we get? 0.01 moles. Why? Because we've applied the recipe because we're at number of moles. Right? So where does that leave us? It leaves us with the last thing is we now can say that, therefore, we've now got a concentration of OH. Let me just put that down there. Concentration of OH is equal to 0.01 divided by 80 milliliters. Because we've added, we had 50, now we've added 30 mils of the acid, right? So we're into 80 mils, which is 0.08, which is going to be equal to 0.125 moles per cubic decimeter. That is the concentration of the OH. And now just recapping again, if we've got that, remember, the concentration of the H3O times the concentration of the OH is the dissociation constant, which is going to be 1 times 10 to the minus 14. Therefore, the concentration of the H3O plus is going to be equal to 1 times 10 to the minus 14 divided by the concentration of the OH, which is 0.125, which is going to be equal to 8 times 10 to the minus 14. Okay? And lastly, we then say, right, the pH is going to be the negative log of the concentration of the H3O plus, which is going to be the negative log of 8 times 10 to the minus 14, which gives us, and you can go check this, 13.1. Right? So that gives us the pH of that at the end of the day. Okay. What I've tried to do with that one is to use a slightly different approach, that if you do get something that hasn't fully completely reacted, you just approach it the same way, bearing cognizance of the fact that there's not the end point of the titration wasn't reached. Therefore, there's a concentration of either the base or there could be a concentration of the acid left. All you've got to look for is you've got to go back to this point here. I'm going to just go back there. We've got to go back to this point here, right there, and look for the limiting reactant, right? Because one of them is used up. In this case, okay, the acid, we only added 30 mil. It had used up, all of it's been used in neutralizing part of the NaOH. However, what has happened is that there's still some OH left, right? Could be the other way if we titrated the NaOH into an acid, right? Therefore, we would know that we've got a volume together, but there's still a concentration of H3O plus in our solution. Okay. I hope those were, well, this one definitely was slightly more above the normal level, but I hope that cleared up if you've ever had one or seen one of these. I hope that's given a slightly different view, but bearing in mind again, all we're doing is exactly the same old thing over and over and over. Just the little trick at the end there. Thanks for watching, and I'm going to be back with redox reactions, and we're going to do quite a lot of those.